The objective of this lecture is to study angular momentum for a system of particles. The starting point for this lecture is as follows. Let P1 through Pn be a system of n particles of masses m1 through mn respectively, and let Ri, for I going from 1 through n, be the position of particle Pi where Ri is measured from a point O fixed in the inertial reference frame I. Furthermore, let Vi in I and Ai in I, again for I going from 1 to n, be the velocity and acceleration respectively as viewed of particle I as viewed by an observer fixed in the inertial frame I. Then the angular momentum of the system of particles relative to an arbitrary point Q in the inertial reference frame I is defined as follows. H, Q, and I is equal to the sum from I equals 1 to n of Ri minus Rq crossed with Mi times V, I and I minus VQ and I. Now the basis of the development in this lecture is going to be to take the rate of change of the angular momentum in the inertial frame. So suppose now that the rate of change of HQi is computed in reference frame I. So this rate of change is given as d dt in I of HQi is equal to. Well, now let's look back at this expression for the angular momentum. We can see that there's a product. In this case, it's a cross product. So we're going to take the derivative of the first crossed with the second plus the first crossed with the derivative of the second. So this is going to equal the sum from I equals 1 to n of Vi in I minus VQ in I crossed with Mi times Vi in I minus VQ in I, and then plus Ri minus RQ crossed with Mi times the acceleration of particle I in frame I minus the acceleration of Q in I. Now you can see that the first term is equal to 0 because Vi minus VQ crossed with Mi times Vi minus VQ is equal to 0. So this thing simplifies to the sum from I equals 1 to n of Ri minus RQ crossed with Mi times AI in I minus AQ in I. And we can see here that now we can split this into two sums. So we're going to actually write this. This is going to equal, I'm going to split this into two sums. The sum from I equals 1 to n of Ri minus RQ crossed with Mi AI in I minus the sum from I equals 1 to n of Ri minus RQ crossed with Mi times AQ in I. Now, let's look at these each individually. So we have two terms. So the first term we'll look at is the term involving it's the first term, first of the summations. So the first summation, let's look at that, the first sum. In this case, we know that from Newton's second law, we have that the resultant force acting on particle I is equal to Mi AI in I. And Ri is the resultant force acting on particle I, on Pi. Now from earlier, the first lecture in systems of particles, we know that Ri is equal to Fi plus the sum from j equals 1 to n of Fij, where Fi is the resultant external force acting on Pi, and Fij is the force exerted by particle j on particle I. Now, we have to actually be a little careful with these forces of interaction between the particles. So we have to state this again, which is that recall that the forces Fij satisfy the strong form of Newton's third law. Namely, that Fij is equal to minus Fji, and Fij, and of course Fji as well, lie along the line of action between Pi and Pj, which we remember that this is the picture, which is that I have mass Mi and Mj, and the force exerted by J on I lies along the line connecting the two. So this is Fij, and then Fji is equal to minus Fij, and this is the strong form of Newton's third law because these two forces lie along the lines connecting these two points. So now, going back to what we were doing. So then, applying Newton's second law, the summation from I equals 1 to n of Ri minus Rq crossed with Mi, Ai, and I is equal to the summation from I equals 1 to n of Ri minus Rq crossed with Fi plus the sum from j equals 1 to n of Fij. And then this can be broken up into multiple terms, which is equal to the summation from I equals 1 to n of Ri minus Rq crossed with Fi plus the sum from I equals 1 to n of Ri minus Rq crossed with the sum from j equals 1 to n of Fij. Now, we can actually rewrite this one more step, which gives the sum from I equals 1 to n of Ri minus Rq crossed with Fi plus the sum from I equals 1 to n of the sum from j equals 1 to n of Ri minus Rq crossed with Fij. Now, because Fij satisfy the strong form of Newton's third law, we have that the double sum from I equals 1 to n of the double sum the sum from I equals 1 to n of the sum from j equals 1 to n of Ri minus Rq crossed with Fij is equal to 0. The reason that's equal to 0 is because we have in each of these terms, we have an Ri minus Rq, and then we have an Fij, and we have a minus Fij because we have an Fji because we're summing from j equals 1 to n. So for every term in this summation that's positive, there's going to be another term in this summation that's going to be negative, which means the whole thing's going to wind up canceling out, and then we're going to wind up getting 0. So then we obtain the following result, that the sum from I equals 1 to n of Ri minus Rq crossed with MI is equal to the sum from I equals 1 to n of Ri minus Rq crossed with Fi. Now let's go to the second sum. The second sum is, so we started with the first sum here. So now let's do the second sum. So the second sum is the sum from I equals 1 to n of Ri minus Rq crossed with Mi times A, Q, and I. But AQ is independent of the summation. So this is equal to the sum from I equals 1 to n of Ri minus Rq times Mi, the whole thing, crossed with AQ and I. But that's equal to, now I can rewrite the sum in the following way. I can put the Mi out front of Ri minus Rq, and I get Ri minus Rq, the whole thing crossed with AQ and I. And now we know that this is equal to the summation from I equals 1 to n of Mi Ri minus the summation from I equals 1 to n of Mi Rq, and then this whole thing is crossed with AQ and I. So therefore, we obtain that the summation from I equals 1 to n of Ri minus Rq crossed with Mi, AQ, and I is equal to, well, the summation of Mi Ri from the definition of the position of the center of mass is equal to Mr bar. And in the second sum, we see that the position of Q doesn't depend on the summation. So we can actually write this, if we want to take one more step, as minus the summation from I equals 1 to n of Mi, the whole thing, multiplied by Rq, and then this whole thing, taking the vector product with AQ and I, which is equal to Mr bar minus MRQ crossed with AQ and I, which is equal to R bar minus RQ crossed with MAQ and I, where we have used the fact that the summation from I equals 1 to n of Mi is equal to M, which is equal to the total mass of the system. So now we can actually write the rate of change of the angular momentum. So using the results from the first and second sums, we obtain the following result. We obtain that the rate of change in the inertial frame of the angular momentum relative to Q in the inertial frame is equal to the summation from I equals 1 to n of Ri minus Rq crossed with Fi minus R bar minus Rq crossed with M, AQ, and I. And Now we can define the following quantity. Now let m sub q equal the sum from I equals 1 to n of Ri minus Rq crossed with Fi. This quantity is what's called the moment due to all external forces acting on the system relative to Q. Now, what we get from that, we can now simplify this to the rate of change in the inertial frame of the angular momentum relative to Q in the inertial frame is equal to the moment due to all external forces relative to point Q minus R bar minus RQ crossed with MAQ in I. Now this is the result that we obtain for the rate of change of the angular momentum relative to an arbitrary point. Now it's a result that actually can be used in practice to be able to solve problems, and we're actually going to do a couple of examples. So here's what we're going to do now is we're going to study 3 examples, and we're going to start simple and we're going to move our way forward to slightly more complicated problems and show you how this works in all these different situations. So the first example is a problem we've studied before in previous lectures, but it's worth studying again because it consists of a single particle and it gives a good understanding as to how to start working with angular momentum. So it's the simple pendulum problem. We've done this one before, as I said, and it's a rigid massless arm suspended from an inertially fixed point O, and at the end of the arm is a particle P of mass m. And what we're going to do is we're going to use angular momentum. So the objective of this problem is to determine the differential equation of motion using angular momentum. Now, in order to be able to do this problem, we're going to actually go about it in the following way. So we're going to do the kinematics, and then we're going to do the kinetics. Oh, and I forgot, there's gravity acting downward. So let's do the kinematics, and we're not going to spend an enormous amount of time on the kinematics because this problem is relatively straightforward. But here's what we're going to do. So we have one rotation, so we need 2 frames. So I is the inertial frame. And then A is equal to the arm. Now the inertial frame has a coordinate system with its origin at O. EX is going to be along OP when theta equals 0. And then EZ is going to be out of the page. And then EY is going to equal EZ crossed with EX. Now let's give ourselves a little bit more room over here. A is equal to the arm. And again, the origin of the coordinate system is going to be at O. ER is going to be along OP. EZ is going to equal big EZ. And then E theta is equal to EZ crossed with ER. So now we're going to use angular momentum, and we're going to use it relative to point O. So we're going to apply an angular momentum balance relative to the hinge point. So how does that work? So the hinge point is actually point O in this case, which means that we need to compute the angular momentum relative to point O in the inertial frame. Well, that's equal to Rp minus Ro crossed with the mass of the particle times Vp in I minus Vo in I. So we're going to need to compute the position of P and the velocity of P. Now we note that because we're measuring from point O, Ro is equal to 0 and Vo in I is also equal to 0. So we need to compute the position and the acceleration. So the position of point P, which is measured relative to O, which is going to be defined as the position of P, the way we laid it out at the beginning of this lecture, that's equal to L-ER. Now the velocity of P in the inertial frame is equal to the rate of change in the inertial frame of the position of P relative to O, which is also equal to the rate of change in the inertial frame of the position of P, but that's equal to the rate of change in the arm of the position of P plus the angular velocity of the arm in the inertial frame crossed with the position of P. So this gives that the velocity of P in I is equal to, well, the first term is 0 because L is constant and ER is fixed in the arm. So this gives theta dot EZ crossed with LER, which is equal to L theta dot E theta. So therefore, the angular momentum relative to point O in the inertial frame is equal to LER crossed with M times L theta dot E theta, which is equal to ML squared theta dot EZ. So now we have the angular momentum relative to point O. So from this, we can actually compute the rate of change of the angular momentum, but we'll get to that in just a second. So for applying an angular momentum balance, a balance of angular momentum relative to point O, what do we get? We get that the rate of change in the inertial frame of the angular momentum relative to O in the inertial frame is equal to the moment relative to point O minus the position of the center of mass minus the position of O crossed with the mass times the acceleration of point O. But we already said that O is inertially fixed, so the acceleration of point O in I is equal to 0 because O is fixed in I. And just for completeness, R bar is actually equal to RP because there's just equal to one. There's just one particle in this in the system, which doesn't really matter in this particular case, but I pointed out just for completeness with the discussion. So in any case, that second term is equal to 0. So R bar minus RO crossed with MAOI is equal to RP minus RO crossed with M times 0, which is equal to 0 because the acceleration of O is 0. So therefore, we obtain that the rate of change in the inertial frame of the angular momentum relative to O is just equal to the moment relative to O. So now we need to compute the moment, so we're going to do the kinetics. Now the kinetics, we have to draw the free body diagram. Of the particle. So if we draw the free body diagram of the particle, here's the particle on the end of the pendulum. We know that mg is acting downward, and we have a reaction force, R. Now, R is equal to R times ER, and mg is equal to mg times EX. Now, you'll notice that R, which is the reaction force, is in the same direction as of the position of P relative to O. So the moment relative to point O is equal to, where do these forces act? These forces both act at point P. So it's RP minus RO crossed with R plus RP minus RO crossed with mg. But the position of P relative to O is actually in the same direction as R, and we'll actually see this here. So the position of P minus the position of O is equal to LER, and R is equal to RER. So that implies that the position of P minus the position of O crossed with R is equal to 0. The next is that RP minus RO crossed with mg is equal to LER crossed with mg EX. If you look at the diagram, you'll actually see that EX is related to ER and E theta as follows. We've got EX, EY, and then EZ, and then we have ER, and we have E theta, and this angle is theta, that angle is theta. So therefore, EX is equal to cosine of theta times ER minus the sine of theta times E theta. So therefore, the position of P minus the position of O crossed with mg is equal to LER crossed with mg times the cosine of theta ER minus the sine of theta times E theta, which is equal to minus mgl times the sine of theta times EZ. So then, and that's equal to the moment relative to point O. So last, let's compute the rate of change in I of the angular momentum relative to point O. That's equal to, well, the angular momentum was ml squared theta dot Ez. So this is equal to, and Ez is fixed in frame A, so this is equal to d dt in A of HOI plus the angular velocity of A and I crossed with HO in I. But this is equal to ml squared theta double dot Ez, and then this is theta dot Ez crossed with ml squared theta dot Ez, and this second term is equal to 0. So this is equal to ml squared theta double dot Ez. So therefore, because the rate of change in the inertial frame of HO in the inertial frame is equal to MO, we obtain that ML squared theta double dot EZ is equal to minus MGL times the sine of theta times EZ, which gives that ML squared theta double dot is equal to minus MGL times the sine of theta, which gives theta double dot is equal to minus G over L times the sine of theta. And that's the differential equation, which is the same differential equation that was obtained when this problem was solved using Newton's second law. Now, let's suppose that we add a little bit more complexity to this. We're going to have another example. Now, in this example, we're actually going to change the simple pendulum problem a little bit. But that little change is going to make a big change to the manner in which we actually have to do these calculations. So in this case, I still have a rigid massless arm, and there's a particle P of mass m suspended from it, and the arm has a length L. This point Q is now not inertially fixed, and it moves with a displacement Q of t. This is known, which is the same thing as it being given. It's a known displacement. And Q of t is equal to 0. Let's write this down. Q of t is equal to 0 corresponds to a point O fixed in the inertial frame. So in other words, what I mean by that is when Q of t is equal to 0, we're going to call that point O. So O is equal to Q when Q of t is equal to 0. That's what I mean by that. And again, we have gravity acting downward, and then this angle is theta. So it's the same setup except for now the pivot point, which is point Q, or the hinge point, slides on this horizontal shaft. And again, we want to derive the differential equation of motion. So this is the objective, is determine the differential equation using angular momentum. Now, how are we going to do this? We're going to do this as follows, which is that we are going to set the problem up in a similar way to the way we set the problem up before, except for now we have this pivot point, which is not inertially fixed. So the kinematics, in this case, are going to be different from the kinematics when the problem was done before. We still have the inertial frame, and we still have the arm. That hasn't changed. But now the manner in which we're going to set up the coordinate systems is going to change. So here's what we're going to do. The origin in this, it's fixed in the inertial frame, is going to be at O, which I remind everyone is equal to Q when Q of t is equal to 0. Again, I'm going to put EX is going to be along QP when theta equals 0. So that's down, if you want to call it that. EZ is out of the page. And then EY is equal to EZ crossed with EX. Now for the arm, again, let me give myself a little bit more room here. The origin is going to be at Q, because Q is fixed in the arm. And then ER is going to be along QP, and then EZ is going to equal big EZ, and then E theta is equal to EZ crossed with ER. So you're going to see that the relationship between the coordinate systems is the same as what it was at least as far as the bases are concerned, is the same as what it was in the previous problem. But now we have to be really careful when we actually apply angular momentum. So we're going to apply angular momentum in this case. Let's see. Apply an angular momentum balance, again, relative to the hinge point. It's exactly the same thing we did before, but in this case the hinge point is equal to q, and q is not inertially fixed. So what that says is that the rate of change in the inertial frame of the angular momentum relative to point q is equal to the moment relative to point q minus r bar minus rq crossed with m, a, q in I. Now let's think about that for a minute. So are if we are applying this moment balance now, remember that Q is the hinge point. So we have to figure everything out relative to the hinge point, not relative to point O. We're not using point O. Point O is inertially fixed. Q is not inertially fixed. So I'm going to write that down. Q is not an inertially fixed point, because you can see that Q is moving relative to the inertial frame. So let's actually start by writing down the angular momentum. So the angular momentum relative to point Q is equal to Rp minus Rq crossed with M times Vp in I minus Vq in I. Now another way that we can actually write that for making things a little shorter is Rp relative to Q crossed with M times Vp in I, Vp relative to Q and I. So we can actually do this a little more quickly if we actually just go straight into this last calculation, which is the position of P relative to Q is equal to LER. Now note, this is not equal to the position of P relative to O, because the position of P relative to O, if we actually look at that, that's equal to QEY plus LER, because that would be measured from point O. Here we're taking the position of P relative to Q. So it's really important that you understand that that's not the same thing as the position of P relative to point O, because I may need that later on. Now the velocity of P relative to Q in I is equal to the rate of change in I of the position of P relative to Q. But because the position of P relative to Q is expressed in a coordinate system fixed in A, that's equal to the rate of change in A of the position of P relative to Q plus the angular velocity of A and I crossed with the position of P relative to Q, where we note now that the position of P relative, we already have it, the position of P relative to Q is already done, so we're going to keep it this way. This is equal to the rate of change of the position of P relative to Q is 0. This gives you theta dot Ez crossed with LER, which is equal to L theta dot E theta. So the angular momentum relative to Q, you'll see it looks the same as what it was in the previous example. It's LER crossed with M times L theta dot E theta, which is equal to ML squared theta dot EZ. So that looks the same as what we had before. But now we're going to have to go about the rest of this a little more carefully, which is we need to start working with the kinetics. So let's look at the kinetics in this problem, and we'll move forward, which is that the free body diagram actually looks the same as what it looked in the previous problem, which is that we had our particle and we have mg acting downward and we have a reaction force r, and r, well, mg was equal to mg ex, and r is equal to r er. So then from that we can actually get that the moment relative to point Q is equal to Rp minus Rq crossed with R plus Rp minus Rq crossed with mg, because both forces act at point P. This is equal to LER crossed with RER, and this is equal to LER crossed with mgEx. The first term is equal to 0, so this gives LER crossed with mg, and then EX is equal to cosine of theta ER minus the sine of theta E theta, which is equal to minus mgl times the sine of theta times EZ. So this is the moment relative to point Q. And you'll see that that looks the same as what we had before. So in the first example, we got the same angular momentum and the same moment relative to the hinge point as what we're getting in this example. But now things are going to change, which is that note in this problem that the acceleration of point Q in the inertial frame is not equal to 0. What is the acceleration of point Q? Well, the position of Q, which is the same thing as the position of Q relative to O, which I'll remind everybody is the position of Q relative to where Q was when Q of t is equal to 0. This is equal to Q times EY. So this gives that the velocity of point Q in the inertial frame is equal to Q dot EY, and the acceleration of point Q in the inertial frame is equal to Q double dot times EY. So therefore, this last term, let's go back here, we notice that we're applying, and we need this last term, which is that the position of the center of mass minus the position of Q crossed with the mass times the acceleration of Q in the inertial frame. This is equal to RP, because that's the center of mass. There's only one particle in the system, minus RQ crossed with M times AQ in I. Now, if we do this calculation, we get that R bar minus RQ crossed with MAQ in I is equal to, well, RP minus RQ is LER crossed with M times Q double dot EY. And that's equal to ML Q double dot ER crossed with EY. Now, if you look at the way EY is defined, if you actually draw that picture, I didn't draw the picture for EX because we didn't really need it because it was the same picture as what we had from before. But here's EY, there's ER, and there's E theta. And this angle is theta because this angle is theta. So this is equal to ML Q double dot ER crossed with, what have we got? We've got sine theta ER plus cosine theta E sub theta, which is equal to ML Q double dot, and now ER crossed with E theta is EZ, and there's a cosine theta in there. So that's the last term. So then we have the following result, which is d dt in I of HQI is equal to, well, it's d dt in A of HQI plus omega AI crossed with HQ in I is equal to ML squared theta double dot EZ plus theta dot EZ crossed with ML squared theta dot EZ, which is just equal to ML squared theta double dot EZ because the second term is 0. So applying a balance of angular momentum relative to the hinge point what do we obtain? We've got d, dt, and I of h, q, and I is equal to the moment due to all forces external to the system relative to point Q minus R bar minus RQ crossed with M, A, Q, and I gives, let's line these up. Here we've got ML squared theta double dot EZ. This is equal to minus MGL times the sine of theta EZ. And then this last term, which is the one we've got here, there's a negative sign, minus ML Q double dot cosine theta times EZ. So therefore, the differential equation becomes ML squared theta double dot is equal to minus MGL times the sine of theta minus ML Q double dot times the cosine of theta. And this is the differential equation. And you'll actually see that this differential equation is different from the differential equation that was obtained when the hinge point was inertially fixed. But you can also see that if the hinge point is inertially fixed, then Q double dot is going to equal 0, and we're going to wind up getting the same result that we got for the actual simple pendulum. So this is the second example. Now we have one more example that we're going to study in this lecture, and that's going to be the end of this discussion for angular momentum. This third example is the following problem. And this again is going to sort of highlight the use of this concept of an arbitrary point, which is, imagine that we have a vertical wall and we have the ground, which is horizontal, and we have an arm that slides while in contact, or I should say moves, while in contact with the wall and the ground. So here is the setup. Let me draw this to make this a little clearer. Okay, so this arm, there's a point P and there's a mass M. There's another point, I'm going to call it Q, and there's another mass M. So there are masses or particle masses at the ends of this arm. The angle that's made by the vertically downward direction and the arm is theta, and gravity acts downward, and contact is maintained, and we're going to assume no friction. So assume no friction. That's important. And the objective is to determine the differential equation of motion using angular momentum. Now, in order to make this description a little bit more complete at the beginning, I'm going to move this gravity. I'm going to move it out of the way, and then I'll put it back. But what we're going to do is, first I want to define a point here. I'm going to call this point A. A lies at the intersection between the horizontal that goes through P and the vertical that goes through Q, and then I'll put gravity over here just to keep it in the problem. And so we know that there's still gravity in the problem. Now, what we're going to do is we're going to actually use A as the point of as the reference point to be able to compute the angular momentum balance. So we're going to first have to do the kinematics, and then we'll do the kinetics. Now, In doing the kinematics, we have to be a little bit careful because you see that there's an angle theta in this problem. So it's tempting to actually do these calculations in such a way that we somehow involve a rotation. And the arm is in fact rotating. But you'll actually see that in this problem, the masses at the ends of the arm are both moving in straight lines. P is moving in a straight line vertically, and Q is moving in a straight line horizontally. So really, the best way to describe this is using Cartesian coordinates. And just to be able to complete the picture here, I'm going to put point O in the corner. And then to label the center of mass, I'm going to call the center of mass point C, which is actually the midpoint because the two masses are equal in this case. So now let's use all this information to be able to solve this problem, and we're going to use an angular momentum balance relative to point A. So here's what we have to do. So the kinematics are going to be done as follows, which is that I'm going to have one reference frame. It's going to be the inertial frame. Even though there is a rotation, we're actually just going to call I the inertial frame. I'm going to put the origin of the coordinate system at point O. I'm going to say EX is going to be along OQ. EY is going to be along OP. And EZ is going to equal EX crossed with EY. Now using that setup, we're actually going to get the following, which is that we're going to use point A as the reference. So we still need to compute the velocity and acceleration of the particle, but we're going to use point A as the reference. And the reason that we're going to use point A as the reference is from the free body diagram. So I know I usually do kinetics a little bit later, but this will actually help identify why we want to use point A as the reference so that that kind of doesn't get left in suspense until the very end. Here's the arm. Now, what are the forces that are acting on this? We have a force of reaction, or normal force, being applied by the vertical wall. We have another force being applied by the ground. And then we have two gravity forces. The first gravity force is being applied at point P, and that's mg. There's another gravity force that's being applied at point Q, and that's also mg. Now point A, if you remember, was this intersection between this horizontal through P and the vertical through Q. This is point A. So as a result, you can see that if we do an angular momentum balance relative to point A, what's going to wind up happening is that all of the forces that go through point A are not going to create a moment relative to point A. So let's write that down. So all forces that pass through point A do not create a moment relative to point A. So what does that mean? That means that any force that passes through point A is going to disappear when we compute the moment. So what are the forces that pass through point A? So the following forces pass through A. One, N sub P. Another one is N sub Q. And actually, and one of the gravity forces, which in this case is the one that passes through, which acts at point Q, and that one actually passes through point A. So the only one that doesn't pass through point A is this force mg, which acts at point P. So as a result, this means that the moment relative to point A due to all forces external to the system is going to equal RP minus RA crossed with MG. That's the only thing that's left. And everything else passes through point A. So let's actually use that information now to be able to do an angular momentum balance relative to point A. So angular momentum balance relative to A. It looks like this. It says that the rate of change in the inertial frame of the angular momentum in the inertial frame relative to point A is equal to the moment relative to point A minus R bar minus RA crossed with M, which in this case is actually equal to 2M times the acceleration of A in the inertial frame. Notice that that's 2M because the mass of the system is actually 2M in this case. So we need to compute all these things. So let's start by computing each piece individually, and then we'll work our way through, which is that, and then we'll substitute in the kinematic results when we're all done, which is that HA is equal to, well, what's it equal to? It's equal to RP minus RA, because there's a mass at point P, crossed with the mass at point P times the velocity of P in I minus the velocity of A in I, plus RQ minus RA crossed with the mass of Q, which is also M, times VQ in I minus VA in I. Now, instead of putting everything in coordinates, let's just look at a couple of things here. If we look back at the picture, we can actually draw this picture over here so that you can actually see it, which is that here is the position of P and here is the position of Q. So let's just diagrammatically. Here's Q and here's P. So if I add the position of P to the position of Q, I get the position of A. So the position of A is equal to the position of P plus the position of Q. And that makes doing some of these calculations actually a lot easier, because the velocity of A and I is then equal to the velocity of P and I plus the velocity of Q and I. Again, we're measuring everything from point O. All distances are being measured from point O. So RP minus RA is equal to, well, it's going to equal RP minus RP plus RQ, which is equal to minus RQ. RQ minus RA is equal to RQ minus RP plus RQ, which is equal to minus RP. And then the same thing goes for the velocity. The velocity of P in I minus the velocity of A in I is equal to the velocity of P in I minus the velocity of P in I plus the velocity of Q in I, which is equal to minus VQ in I, and the velocity of Q in I minus the velocity of A in I is equal to the velocity of Q in I minus the velocity of P in I plus the velocity of Q in I, which is equal to minus the velocity of P in I. So therefore, the angular momentum relative to point A and I is equal to, well, let's start substituting. RP minus RA is equal to minus RQ. So you get minus RQ crossed with M times minus VQ in I. And then I get plus, and I'm going to do minus RP crossed with M times minus VP in I. Now look at something. You'll notice that RQ and VQ are in the same direction. RQ and VQ in I are in the same direction. Which implies that RQ crossed with VQ in I is equal to 0. RP and VP in I are in the same direction. Which implies that RP crossed with VP in I. There's a scale factor of M in here, but M can just be brought out front, so it doesn't really matter, is equal to 0, which says that the angular momentum relative to point A is equal to 0. So we now have the angular momentum relative to point. So the first thing we got, which is in this first line up here on this previous page, the rate of change of the angular momentum is equal to 0. So the rate of change in the inertial frame of the angular momentum is equal to 0. So we're done with that. Now we need the moment relative to all forces. So now what we can do is we can actually start to work with coordinates a little bit, which is, remember that we had that the moment is equal to RP minus RA crossed with mg. So the moment relative to point A is equal to RP minus RA crossed with mg. But we know that RP, let's go back to the diagram, and we can see from the beginning what RP is. RP is equal to L times the cosine of theta times EY. So RP is equal to L times the cosine of theta times EY, and RA is equal to, what's RA? Well, let's get RQ, because we need that for RA. This is equal to L times the sine of theta times EX. Now we know that RP minus RA is equal to, well, let's go back to what we did before. It's equal to minus RQ. So that's equal to minus L sine theta times EX. And then we also know that mg is equal to minus mg EY. So this implies that the moment relative to point A is equal to minus L sine theta times EX crossed with minus mg EY, which is equal to mgl times the sine of theta. EX crossed with EY is EZ. So there's the moment relative to point A. So now we have the first two terms in this top line. We have the rate of change of the angular momentum, which we know is equal to 0, and we have the moment relative to point A. Now we have to figure out the rest of these. We have to figure out R bar minus RA crossed with 2m times the acceleration of A. So next, we need R bar minus RA crossed with 2m times the acceleration of A in I. So what's R bar equal to? So let's do that first. So R bar, which is the position of the center of mass, is equal to the first mass times the position of P plus the second mass times the position of Q, all divided by the sum of the two masses, which is equal to 2m. So this is equal to RP plus RQ, all divided by 2. What that's equal to, well, we can do that afterwards, because we can first compute R bar minus RA. So that's equal to RP plus RQ, all divided by 2, minus RA, which is RP plus RQ, which is equal to, well, if we do this calculation, we've got RP over 2 minus RP, which gives us minus RP over 2, and then minus RQ over 2. But if you look at that, that's equal to minus R bar. So RP or r bar minus RA is equal to minus r bar. So we actually have a nice simple expression in this case for r bar minus RA. So now we need the acceleration of A. So this is r bar minus RA is just equal to minus r bar. So next, the acceleration in A of A and I is equal to the acceleration of P in I plus the acceleration of Q in I, because the position of A is equal to the position of P plus the position of Q. So this is equal to, now we can actually start to work with this, right? So the acceleration of P in I is equal to, well, we have to get the velocity of P in I first. So let's get the velocity of P in I. The velocity of P in I is equal to minus L theta dot sine theta times E y. And the acceleration of P in I is equal to minus L times theta double dot sine theta plus theta dot squared cosine theta times E y. So that takes care of point P. The acceleration of Q in I is equal to L theta dot cosine theta times EX. So this is not the acceleration, it's the velocity of P and I. Skipped a step here. And then the acceleration of P in I is equal to L times theta double dot cosine theta minus theta dot squared times the sine of theta times EX. Now, we can use that to be able to figure out the acceleration of A. So therefore, the acceleration of point A in the inertial frame, which is equal to the acceleration of P in the inertial frame plus the acceleration of Q in the inertial frame, is equal to, so if we write this down, we've got minus L times theta double dot times sine theta plus theta dot squared times the cosine of theta times EY. And then we've got plus L times theta double dot cosine theta minus theta dot squared sine theta times EX, which can be rewritten as L times theta double dot cosine theta minus theta dot squared times the sine of theta times EX minus L times theta double dot sine theta plus theta dot squared cosine theta times EY. So that's the acceleration of A. Now what do we need here? We need to take r bar minus RA crossed with 2m times the acceleration of A. But now we can actually look at this point r bar, and we can actually see something about it, because r bar minus RA is equal to minus r bar, and r bar is equal to minus RP plus RQ over 2. So because r bar is equal to RP plus RQ over 2, that implies that r bar is equal to, well, it's equal to L over 2 times, well, RP is equal, there's L cosine theta EY, and then sine theta EX, which implies that r bar is equal to L over 2 times sine theta EX plus the cosine of theta EY. And that is equal to, well, that's, and minus r bar is equal to minus L over 2 times the sine of theta EX plus the cosine of theta EY, which we remember is equal to r bar minus RA. So then r bar minus RA crossed with 2m times the acceleration of point A in the inertial frame is equal to? Well, r bar minus RA is equal to minus L over 2 times sine theta EX plus cosine theta EY, and then crossed with 2, let's put this on the next line, crossed with 2m times the acceleration. But the acceleration in A is equal to L times theta double dot cosine theta minus theta dot squared times the sine of theta, and then that's times EX, and then minus L times theta double dot sine theta plus theta dot squared cosine of theta times EY. Now what's that equal to? Well, let's see here. We've got L over 2, we've got a 2m, so there's an L squared and there's a 2m, so the 2 drops out. So we've got an mL squared. And let's see what happens when we actually do this. This is minus mL squared because of all the factors. And actually, you know what? Let's not do the minus mL squared yet. Let's just keep everything the way it is. So I've got minus L over 2, which is out front. And this is multiplied by 2m. So I've got 2m, so I've got minus mL. So that's all the way out front. And now let's do this. I've got EX crossed with EX is 0, EX crossed with EY is EZ. So I've got minus L times theta double dot sine of theta plus theta dot squared cosine of theta. That's times the sine of theta, and that's times EZ. And then I've got, that's EX crossed with EY. I've got EY crossed with EX, which introduces another negative L. And then I have EY crossed with EX gives me theta double dot cosine of theta minus theta dot squared times the sine of theta, and then times the cosine of theta times EZ. Now we can actually see that there are negative signs everywhere that all cancel out. We get mL squared. And what are we left with? We're left with theta double dot times the sine squared theta, and then we've got plus theta dot squared cosine of theta times the sine of theta, and then we've got plus theta double dot cosine squared theta, and then we have minus theta dot squared cosine of theta times the sine of theta, the whole thing multiplied by EZ. So you can see that the theta dot squared terms cancel out, and sine squared theta plus cosine squared theta is equal to 1. So that implies that r bar minus RA crossed with 2m times the acceleration of A and I is equal to mL squared theta double dot. So now we have everything. We have the moment, and we have everything else. Where's the moment? The moment is mgl times the sine of theta. So this gives that 0, which is equal to the rate of change of angular momentum, is equal to the moment relative to point A. I'll label these again just so that you can see it. mgl sine theta EZ, and then plus, this is times EZ, and then this is actually times EZ also, and then plus mL squared theta double dot times EZ. So this gives that the differential equation is mL squared theta double dot, and then we've got plus mgl times the sine of theta is equal to 0. And let's just make sure that we got the sign right here on this gravity moment. So this is minus mgey. So we've got minus L sine theta. Ex crossed with ey is ez. And we've got mgl times the sine of theta. And that's correct. That's the moment relative to point A. And then we also have the fact that this term over here is this is where the issue came in, which is that this actually is supposed to be a minus sign because we have a we have a we have a negative sign in the angular momentum balance. So this should actually be a minus sign. So actually, to be able to see that, and then this here should actually be a minus sign. And to be able to see that, let's look at this equation a little bit more carefully just to make sure that we actually did everything here correctly. Let's bring this down here so we can see it again. This is equal to mgl times the sine of theta times ez. What's this here? This term here is the rate of change in the inertial frame of the angular momentum relative to I. This term right here is equal to the moment relative to point A, which is what I computed before. And then we have minus ml squared theta double dot times Ez. Now what's that term? That whole term, including the negative sign, is equal to minus r bar minus ra crossed with the mass times the acceleration of A in I. So that's where I got all that stuff from. So this last result becomes the differential equation. So we get that ml squared theta double dot minus mgl times the sine of theta is equal to, and you actually can see that when you do all this, see the 2 actually drops out with the m, and this is equal to 0, and that is the differential equation. So in this lecture, we actually did 3 examples of varying levels of complexity to be able to show that how angular momentum works in systems of particles. And these results are very situational in the sense that every problem is a little bit different, so you have to go about it a little bit differently. But hopefully these 3 examples provide some insight as to how to go about solving problems using angular momentum for a system of particles. And that's going to be the end of this lecture. And in the future, we'll actually continue using angular momentum in other ways when we study it, both in the context of systems of particles and ultimately in the context of rigid bodies.